Hello everyone, and welcome to the third part of wind load generation in STAAD.Pro Connect Edition. I am Surajit Ghosh, and in this video, I'll cover how we can generate wind load on any unclad frame structure like a Piperack using the newly implemented wind load generator. For this type of structure, several information is required, including solidity ratio and shielding factor. How we can calculate and use this for load generation, that I'll cover in detail. In last two parts of this series, I have covered the basics of wind application and used the wind load generator to apply load on different type of structure, including a cladded building and a pitched roof warehouse on wall, roof, overhang. You can check those for more details. Apart from cladded building structure, another common type of industrial structure is the unclad frame structure like a coal handling unit, conveyor belt, pipe rack or temporary frame structure. There is no external cladding, hence wind is applied directly on the member. For such type of unclad frame structure, we need to consider wind load as member load. Also, calculation of load intensity is different from a cladded building structure, as we need to consider several additional factors like solidity ratio and shielding factor. Do you know, using wind load generator, we can generate complete wind load specification for any unclad frame structure? Consider this pipe rack structure. It is an exposed steel frame without any cladding, which supports several pipes with variable diameter at different level. These pipes are modeled and analyzed in AutoPipe. Then those information including support data are imported in STAAD using STAAD AutoPipe link. As you can notice, all these pipes are correctly placed on the frame with proper connection. Now I want to design the frame based on the pipe stress and other force including wind. Earthquake and pipe loads are already added. These pipe stress are imported from AutoPipe as a reference load. Then it is used for structural analysis. As it is an unclad structure, wind load should be applied directly on the member as UDL. First, I want to add wind load from X direction. To generate this load, once again we can use the wind load generator. This time, we will use unclad frame building. In this page, all these inputs are similar to cladded building structure. These are required for wind intensity calculation. In part 1 and 2, I have covered how these inputs are used to calculate the wind intensity at different height and location based on IS875 part 3. K1 to K4, KD, KA and KC can be defined using this parameter like basic wind speed at the project location, risk, topography and importance factor, terrain category. On basis of this, wind intensity at specified height interval is computed till the maximum height of the structure and added to the model under wind definition. If required, program generates multiple wind definition for different direction. Till now, there is not much difference in calculation between a clad and unclad structure, but how the wind load is transferred to the member, that is different for an unclad frame building. For any cladded structure, clause 7.3.1 or clause 7.4 is used to calculate the wind load on individual element like wall, roof or member, where A is the surface area of cladding unit. Load is applied on the cladding and then transferred to the supporting frame as nodal or member load. For an unclad frame building, clause 7.4 is used, but as there is no cladding, load is applied directly on the exposed member, on the face which is in the wind direction. Cross-section area of the face is used to calculate the member load intensity, which is applied as an UDL. Force coefficient for any unclad building is calculated using clause 7.4.3, either from table 31 for single frame or from table 32 for multiple frame. If we look at this table, we can notice that force coefficient depends on the solidity ratio, frame spacing ratio, and exposed surface type, whether the member cross section is flat or circular. For multiple frame building like this Piperack structure, based on the effective solidity ratio and distance between the frame, shielding factor is calculated. Then it is multiplied with the force coefficient mentioned under table 31 to find the correct coefficient. We can specify all these values in the wind load generator. Few are automatically generated based on the model data. Few are user input. Inputs in this page is different from a cladded building. All building related data are now replaced with input required for frame building as suggested in clause 7.4.3 of IS875 part 3. Using this, we can generate wind load on any frame from a particular direction, positive or negative X or Z. For this model, I will generate wind load from positive X direction. We need to provide the number of frames along the wind direction which are subjected to wind load. For this model, there are 6 frames along Z direction which will be subjected to wind pressure. Distance between the frames are automatically computed using the model data along with other dimensions. If required, we can edit this or provide spacing ratio. As load is applied on the member, load intensity depends on the cross-section area. Both flat and round cross-section can be used. For this model, eye and angle section are used. We can select flat-sided member. Next, we need to provide the force coefficient, which is very important for load generation, and depending on this, wind load intensity on a member is calculated. Either we can specify solidity ratio and shielding factor, or directly provide the force coefficient. Solidity ratio defines how much area under a frame or roof is covered for wind flow with other object or obstruction. Under clause 7.3.3, how this is calculated for a canopy roof, that is covered. Basically, it is the ratio of total area of obstruction divided by the gross area under the canopy in the wind direction. Consider this building. When wind flows from X direction, it cannot enter inside the structure due to the solid full height wall. Hence, the effect of wind on various structural components is minimized. For such case, area of obstruction is same as the gross area. Hence, the solidity ratio is 1. But if we consider the wind flow from Z direction, there is a large opening through which wind can enter. For Z direction wind movement, solidity ratio is the area of the solid wall divided by the gross surface area, which is less than 1. If there is full opening or no obstruction to wind flow, then it is equal to 0. When you consider wind flow on any frame structure, load is applied on the first frame in the wind direction, then it flows under and around the frame. If there is any object present under the frame, like a pipe for this model or packing box for any warehouse building, that will resist the free flow of wind. Also, location, orientation and dimension of any member like beam, column or bracing affects the wind flow. Wind is diverted if there is any cross bracing or secondary member present in the frame. Similarly, if a wide section is used as column or beam, or the higher section depth is oriented across the wind direction, obviously that will resist the wind movement. Hence, next frame in the wind direction will not be subjected to full pressure. More obstruction means less wind flow. How much pressure is distributed to the next frame? That is governed by the solidity ratio of the previous frame. For example, consider the first frame. There is only one pipe moving through this. Hence, there is negligible obstruction to the wind flow, and second frame will be subjected to almost full pressure load. To calculate the solidity ratio, we need to calculate the total obstruction area. sum of member cross-section area plus the pipe area and divide it with the total area under the frame. It is close to 0.1. But if we consider this bay, there are multiple pipes. Wind flow will be resisted by this. For frame 3, total area of all the pipe plus member area divided by the area under the frame will provide the solidity ratio, which is approximately 0.3. We need to provide all this value for each frame at each level in this table. Along with this, we need to provide the effective solidity ratio. As per clause 7.4.3.4b for flat-sided member, this is equal to the solidity ratio. Hence, we can specify same value at each level. Based on this and frame spacing ratio, shielding factor is calculated from table 32 and force coefficient is calculated from table 31. This force coefficient is used to calculate the total wind load acting on a member using clause 7.4. I think it is clear now how these force coefficient are calculated and used for load generation. Finally, we need to assign this load on the frame member, either using a group name or member list. Also, we can simply provide the range. Program internally finds all the member within that range and apply member load with calculated intensity. I want to apply wind load on all the members, so we can skip this input and generate the wind load. As you can notice, a wind load case is added to the model with load from positive x direction. All members present in this model are loaded with UDL. We need to refine this assignment with proper range or member list. Similarly, we can generate wind load from other direction like Z or -x. By the way, when we use this wind load generator, relevant wind definition is generated with different height versus intensity data. Using this method, we can generate wind load for any unclad frame structure with wind load generator. There is another approach. We can automate wind definition and add all loads manually. Since V22 Update 8, wind definition page is updated with IS875 Part 3. If we select this code, we can populate height versus intensity data using auto-generation option. Here, both this cladded building and unclad frame option are available. This is only for wind definition. No load is added to the model. We need to manually add the loads. Better use the wind load generator. Along with this, there are two additional types, lattice tower structure and freestanding wall or hoarding. For any tower, we can easily generate the wind definition using this widget by providing few information about the tower like cross-section and solidity ratio. Once the wind definition is generated, we can use that for load application. If you want to know about this feature, let me know in the comments. I have covered few common types of industrial structure, but there are several other shape and combination of structure like a platform set, which is a free monoslope structure with steel column subjected to open wind load. Load generation process is similar to our discussion. We might need some additional step. That's all for today. Thanks for watching.